Hi ladies, this is lesson 7.2, and this lesson is about exponential functions, and specifically today we're looking at exponential decay functions. So if you remember from the last lesson, we looked at exponential growth functions, where the function would grow exponentially, it would approach infinity, but it would never get less than 0. Well, in this case, it's going to decay exponentially, but it's never going to actually reach that asymptote, which is y equals 0. So it's never going to be 0, but it's going to continue to get smaller and smaller and smaller. So an exponential decay function is going to be written in the form y equals a times b to the x power. But here, a has to be greater than 0 still, just like in our exponential growth function. But b is going to be between 0 and 1. So with an exponential growth function, b was greater than 1. Here, it's going to be less than 1, but it's still going to be greater than 0. And then the decay factor is our b. Just like our growth factor in our exponential growth functions was that constant b. So if you look at your note sheets, here is the parent function for an exponential decay function. So again, it's in the form y equals a times b to the x power. But the difference is that b is between 0 and 1, which makes it decay exponentially. So here we have our asymptote, and that's the x-axis. So it's going to continue getting closer and closer and closer to the x-axis, but it's never actually going to be, our function's never actually going to be equal to 0. And the graph, it falls from left to right, and it passes through the points 0, 1, and 1b. Looking at the domain and range, the domain is all real numbers, and the range is y is greater than 0. So if you remember from our exponential growth function, our range was the same, y was greater than 0, but it was like a reflection of this graph, where as x got larger, the function would continue to grow, but here, as x gets larger, the function gets smaller. Right, so let's look at a couple examples. So in this first example, this is an exponential decay function, and you know that because here's your b, it's less than 1. 3/4 is less than 1, and it's greater than 0. Therefore, well, actually, this is not an exponential decay because your a is not greater than 0. So it's going to be a reflection of an exponential decay function. So let's first look at this function, and let's define our domain and define our range. So because a is less than 0, this is not an exponential decay function. But in this function, looking at our domain, our x value can be any real number. Any real number that we pick for x is going to output a real number. And then looking at our range is going to be a little bit different because we're multiplying by a constant of -2 instead of constant of 2. So that 3/4, as x gets larger, that 3/4 is going to get 3/4 to the x power is going to get closer and closer and closer to 0. So our range is going to be y is less than 0. And we can plug in a couple points to see that. So again, we're going to use 0 and 1. If our x value is 0, then our y value is -2. Because 3/4 to the 0 power is 1. -2 times 1 is -2. And then if we plug in +1 as our factor, -2 times 3/4 is -6/4, or -1.5. Okay, so if you look at this, and we know that we're going to get closer and closer and closer to 0 as our x values increase, our function is going to look something like this. And you can plug in more values to get a more accurate graph, but we know that as just by using logic, as x gets closer to 0, and you can plug in a couple numbers to verify, but as x gets closer, or x gets higher, y gets closer to 0. That's why our range is y is less than 0, because this whole graph is below the x-axis, but it gets closer and closer and closer to that x-axis as our x values increase. Okay, let's look at the second example here. We have it in the form a times b to the x minus h plus k, where h is our horizontal shift, and k is our vertical shift. So if you look at this function, our a is greater than 0, and our b is less than 1, but it's also greater than 0. So this function is exponential growth, exponential decay. So as our x values increase, our y values are going to get closer and closer and closer to 0, but they're never actually going to reach 0. So when we do this, our first step is to graph the function a times b to, or b to the x power, a times b to the x power. And then our second step is to translate the points. So our first step, we're going to graph a times b to the x power, which is 2 times 3/5 to the x power. So we'll pick a couple points, 0 and 1. So when x is 0, y is 2. And when x is 1, y is 6/5, which is 1 and 1/5. So right about here. And then we're going to draw that curve. So it's going to go through these 2 points, and it's going to get closer to the x-axis, but it's never actually going to approach it. Or it'll approach it, it'll never actually reach it. So here's our curve. And now we're going to translate these points by h and k. Our h value is +1, and our k value is also +1. So we're going to translate this graph, each point, 1 unit to the right, and 1 unit up. And then we're going to draw our new graph. Then we can state the domain and the range. And this is for the function 2 times 3/5 x minus 1 plus 1. The domain for this is all real numbers. X can be anything. But the range, since we shifted that parent graph up 1 unit, our y is going to stay above 1. So our new asymptote is right here, where y equals 1. It's never actually going to reach that point, no matter how high our x value gets. It's never going to output a value of 1. It'll get really close, but it will never actually be 1. This next part of the note sheet is the your turn part, so please pause the video while you work, and you can unpause for the solution. Notice just before you start that this first a value is -2, so it's neither an exponential growth or an exponential decay function. So graph accordingly, it'll be a reflection over that x-axis. And then in the second one, notice that you have an h and a k value. So pause the video while you work, and when you unpause, you will see the solution. So in this first example, you have y equals -2 times 4/5 to the x power, where your a is negative. So this is neither an exponential growth or an exponential decay, but it's going to, as your x values increase, your y values are going to get closer to 0. So you'll pick 2 points, x is 0, x is 1. And when x is 0, y is -2. When x is 1, y is -1.6. And you'll graph those 2 points, and then again, your asymptote is the x-axis. So your range is y is less than 0. So in your whole function, you're below the x-axis. Your first step in this second problem is to graph y equals a times b to the x power. So you're just graphing 3 times 2/3 to the x power. And you get 2 points. When x is 0, y is 3. When x is 1, y is 2. And then your second step is to translate by h and k. So you need to identify your h as -1 and your k as -3. And you're going to shift each of those points to the left 1 unit and down 3 units. And then you can identify your domain and your range for that whole function. So your domain is all real numbers, and your range is y is greater than -3. This next example is a multi-step problem. So the problem says that a new television costs $1,200, and the value of the television decreases by 21% each year. So we're going to write an exponential decay model giving the television's value in dollars after t years, and then we're going to estimate the value after 2 years. We're going to use this graph to graph the model, and then estimate when the value of the television will be about $300. So in this problem, we need a general formula for exponential decay. So let's think first about our exponential growth model. And for that model, we used y equals our initial quantity of something, or initial amount, times 1 plus our growth rate to the t power. So now that we're looking for exponential decay, we're getting closer to 0. So exponential decay model, we're going to use the model y equals a times 1 minus r to the t power. Our variables are all the same, where y is the end amount, a is our initial amount, r is our rate as the decimal, and t is our time in years. So for this particular example, if we're going to write an exponential decay model, where our model is y equals a times the quantity 1 minus r to the t power, in this example, our a is the initial cost of televisions, which is $1,200. Our r is 21%, which is 0.21. And our time is 2. We're looking for it after 2 years. So then y equals 1,200 times 1 minus 0.21 to the second power. And we get y equals $748 and 92 cents. So we can graph that. So after 0 years, we have 1,200, but after 2 years, our television's only worth about $750. And you can plug in a few other values here too to get a more accurate curve. So I just plugged in a couple more values. So when t is 4, so after 4 years, our TV is worth $467. So about there. And then after 6 years, about $291. And then after 9 years, $143. So then I can draw my curve that includes all of those points, and that gets closer and closer to 0. But again, it's never going to actually be worth $0. Try this next one on your own. You can pause the video while you work. So you're using that same model from example number 3 that we just did together, but now you're using a 12% decrease each year. So now your model is y equals 1,200 times 1 minus 12%, or 0.12 to the second power. And if you're looking for how many years it's going to take to reach about $300. So when your y value is about $300, your time is somewhere in this range. So sometime between 10 and 11 years. So again, the more points that you plot on a curve like this, the more accurate your curve is going to be. At the very least, you should look at the graph and plot the very first point, some point in the middle, and then an end point, so that you know exactly how steep your curve is going to be. So please jot down any questions you have from this lesson, and we can go over them in class next time I see you.